Ladies and gentlemen, I now call upon Professor Smoot to come to the podium to deliver his lecture. Thank you, sir.
Salam, Your Royal Highnesses, honored guests, ladies and gentlemen. It's an honor and a pleasure for me to be here. And let me try and get this to start. It takes a second. And I will have to apologize for the first slide, because I should have said Putrajaya instead of Kuala Lumpur. And I know the difference. I'll fix it after the lecture. But I always had on my list to come to Kuala Lumpur because it sounded so exotic. But now that I know of Putrajaya, I should have put it on the list too. So I want to talk about contemplating the verse of the universe, but I want you to see how it is we actually dare to contemplate that and think that we can measure it and observe it and actually know what we're talking about. And so I thought the best analogy I could make is to CSI, the crime scene investigation, but this time a cosmic scene investigation. And so one of the things we do is we look around this room, and if we're true cosmologists, we can explain everything in this room, not in detail, but where all the elements came from that made up the things that are in this room, including me and the podium and everybody in the audience. So part of our goal is to explain everything in the universe. It's a mild goal, but that's what we want to do. Do I have a laser pointer? Oh, wait a minute. I found my briefcase. So we can do this. So I wanted to show you a picture of cosmologists at work. You can recognize they're cosmologists because they have laptop computers that they're carrying around with them. And they have certain approaches that they have, which is we collect evidence. That is, we look around us and see what we can see, and we gather this evidence, and we see from this evidence the relics of creation and the relics of the development of the universe after that point. And the next thing we do is we build special tools. And so I have to confess, I had the foresight to see that cosmology was a field that was ripe for development, but it took me 2 decades to build the tools and to get the procedures and to make it so it's possible to realize the thing we're doing. So sometimes it's easier to envision what you need to do than to actually do it. But if you stick to it, you can actually do that. So we developed a lot of tools and a lot of special procedures for how to take data and understand it. But once we had good quality data in hand, then we use computers to analyze that data. Then we make up models, and we run computer simulations and compare the models that we put in our computers to our observations and see what is the best description of the universe we observed around us. And you see, if you watch the CSI series, they do that in a more theatrical sort of way, but that's what they're doing. Okay. Now, this year is a special year, and this is actually very close to the 400th anniversary of the time Galileo built his own telescope and was the first person to point a telescope at the heavens. Before that, people were using naked eye observations. But Galileo we pull out, especially because it's 400 years ago, and because he also helped us develop the ideas of the laws of motion and the scientific method, the careful, rational thinking about observations and the world around us and applying that to what we see. It's not to say astronomy started with Galileo, because we know astronomy that all ancients were doing it. The Babylonians, there was a spectacular resurgence of astronomy under the Muslims 1,000 years ago, and Al-Mamun has actually 2 craters on the moon named after him. He founded the library and 2 observatories 1,000 years ago and started the collection of observations that led to this sort of thing. But it was Galileo followed by Newton, who showed that gave us the ideas we could describe nature with more than just observations and summing up the observations, but by actually making models that we could compare to the observations and save the phenomenon that we saw in very simple coding. And so Newton made his laws of motion, and he made the thing that we call the first universal law, Newton's universal law of gravitation, where he explained the motion of the moon, and then explained it to other planets, and eventually to the stars out in the universe. Now I'll show you another picture. The telescope you see over there, the telescope you see over here is a very simple, weak telescope. It was only a factor of 2 improvement. Galileo was able to make some astounding discoveries. He discovered 4 moons of Jupiter. He saw the phases of Venus. He saw the moon had craters. Just that extra bit of resolution did that. Now we build much greater tools in order to collect our evidence. So here's the Hubble Space Telescope, and here's a deep field picture from the Hubble Space Telescope. And can I have the lights down in the front some? In this picture, the thing that's remarkable about it is you can only see 4 stars. This is a star, this is a star, this is a star, and this is a star over here. Hopefully we can get the focus a little better too. And if you look, everything else in this picture is a galaxy. That is a collection of stars, and it's a very large collection of stars. This galaxy over here is a spiral galaxy. It's very much like the galaxy we live in. We think it has about 100 billion stars in it, just like our own galaxy. So when I look at this picture, I wonder, are there intelligent beings in that galaxy, wondering where the universe came from and how they can describe it? And are a few of them looking at our galaxy, studying our galaxy to see what we can understand? But if you look around, you'll see there are these galaxies, and some of them are yellow-colored, like our sun. Those galaxies, it turns out, when you study them carefully, tend to be closer to us, and they tend to be more evolved. And it's not a surprise. The ones that are closer to us, you'll understand in a couple of minutes, the light is coming to them much later in the history of the universe than the ones that are very far away, because it takes light so long to travel. So the ones that you see behind it are smaller and more irregular. They're smaller because they're further away. They're smaller because they're younger and they haven't merged together. But they're yellow. They're not yellow. They're white and blue, which is surprising. It means their stars are burning much more fiercely in those early galaxies, and much more fiercely because we actually know the universe is expanding, which I'll tell you about. So the light should be shifted to the red. So the fact that they're still white and yellow. So from this picture alone, which you could go on and talk the whole talk on, you're able to understand a lot about the universe, and it's simply a matter of collecting good data and observing it and thinking about it carefully. That's the whole process. Now the next big step was taken as a result of the work of this man, Albert Einstein, who Time magazine named this person of the century. Undoubtedly, if they had existed earlier, they would have named Galileo or Newton the person of their century. And of course, we're looking for the person of this century because now we have great new discoveries, but we have great new unknowns that we need some genius or some new generation of scientists to help us solve. But the thing that Einstein did that was most impressive, that lets us think we can attack the problem of the universe as a whole, was he published a theory of the general theory of gravity, the general theory of relativity, and he published that in 1915. And in that, there's a lot of interesting things. The equations that say the curvature of space-time is set by the matter-energy content, and so putting matter in space-time tells space how to curve, and the curvature of space tells matter how to move. So anything that acts always has a reaction, and that happens. But the other thing is, as soon as you introduce curvature of space, you introduce a scale to space, and then as a result of that, you can have that scale change with time. That is, the universe can be expanding or contracting. And there were 3 people who found solutions to Einstein's problem: George Lemaitre, Alexander Friedman, and Wilhelm de Sitter. And George Lemaitre wrote an article, and then he wrote a letter to Einstein, enclosing the letter in the article, and mailed it to Einstein. And Einstein read it, and here's a picture of Lemaitre and Einstein at that epoch. So Lemaitre down here, Einstein on the top, and he said, "Your mathematics is correct, but your physics is abysmal, because everyone knows the stars are fixed in the sky. If you're a shepherd or a person who goes out and observes, every year you see the same set of stars progress across the sky. They're pretty much fixed night after night, and they just move slowly over the year, and they come back and start all over again." And in fact, the word planet, the word we use in English for the things in the solar system, means wanderer. That is something that moves relative to the stars. Every human knew that the night sky does not change except for very few things, and those are unusual objects. And so everyone knew the universe was static, And so the fact that the universe could be expanding and contracting, Einstein could not accept. He went and modified the general theory of relativity and added another term to it. And that ended up with another solution that also has the universe expanding. And that also got Einstein upset. And but later on, he reconciled. So there's a picture later on with Lemaitre and Einstein and Millikan, who did the oil drop experiments, and also the Center and Friedman, who found other solutions that had expanding and contracting universes, but mostly expanding universes. And they did that because the astronomer Edwin Hubble, after whom the Space Telescope is named, discovered that the universe is expanding. So, but before I get to that, I want to be very careful about one idea, and that's the idea about what the Big Bang means, because it's a lovely name, but it's misleading. Right? So here's a picture that was made by a former student of mine and his graduate student, and published. And this is the idea of how you can understand that it's not that here's space existing and then all the galaxies were clumped in the middle and they blew up and flew out. That turns out to be far from what's correct. But in fact, if the galaxies are already there, space itself is expanding between the galaxies. The galaxies themselves are not moving. And so space is three-dimensional, but to show it to you, I have to go to 2 dimensions. So we imagine that we're confined to the surface of a sphere, and that sphere has a certain scale factor, namely its radius. And you can look at it at different epochs. And so if you look, there are grid lines. Let me see if I can focus this. Well, I don't know if I can focus it. I should leave it alone until we see. It's slightly distorted. But there are grid lines, and if you will follow the grid lines, you will see this galaxy stays at the intersection, stays at the intersection, stays at the intersection, independent of the scale. That is, this galaxy, if it looks at the space around it, thinks it's not moving, right? It's just the space is expanding. But if it looks around it, it sees space at rest very close to it, and a little further out, the space is moving a little away from it. Further out, it's moving further away from it. Likewise, this galaxy is on a coordinate crossing and a coordinate crossing and a coordinate crossing, if you could see the focus a little better. And it is, in both cases, neither galaxy believes it's moving, because it's not moving relative to the space around it. Yet the space is growing in between it. So this is not a case of objects flying out into pre-existing space, but space itself expanding. So it's not an explosion in the conventional sort of sense. Now you have to imagine this in 3 dimensions instead of 2, but that's, or an infinite plane instead of a spherical surface. Okay, so now to the discovery that reconciled it. Edwin Hubble was the astronomer who started studying what were called nebulae or clusters, and he was able to show that some of them were star clusters in our own galaxy, but many of them were too big and too far away to be in our own galaxy, but they were galaxies of their own selves. So he established the field of extragalactic astronomy. He started studying where they were, and after a little bit of more observations, he was able to show that the galaxies are moving apart from each other. Right? And so let me show you his first data, because this becomes the second universal law. His data is if you measure the distance to the galaxy and then measure the rate at which they're moving apart, and this is in kilometers per second, you can plot it up, and depending on whether you look at galaxies as individuals or as groups, you get 2 things that he drew, 2 lines that he drew. And he said, there's a linear relationship. Well, you'll notice there's a couple galaxies moving towards us, but all the other galaxies are moving away from us. And the way you do that is you just look at a galaxy, and you see how big and bright it is, like this one, and you look at the absorption lines of calcium atoms in that galaxy, and you can measure whether those lines are where they are at the Earth or they're shifted. And if the universe is, if things are moving apart, there is effectively a Doppler shift. The wavelengths change. And so if you look at galaxies that are further and further away, you can see these lines move to the right. They get to longer wavelengths. So you can measure the apparent size and the apparent brightness, and that tells you an estimate of the distance. And you can measure the shifts in the wavelength, and that tells you the rate at which things are moving apart. And you find this linear relationship. This was the early data. Here's some somewhat later data, where now you're looking out to 1,000 million light years, or 1 billion light years, and you're looking out to velocities that are 20,000 kilometers per second, almost to 30,000 kilometers per second. You find this very nice straight line.